This lesson will focus on position time graphs, mostly on looking at the displacements and an overall consideration to help us describe scenarios. So you can see here I've got a little quick example of a distance time graph. So we're starting with distance with no direction, and it's in meters and the time is in seconds, and it's just a rough sketch there showing that we can represent motion with a graph. You can see the vertical axis represents distance, the horizontal axis represents time, and this can only be used to represent motion in one direction, okay, or in a scenario where the direction doesn't matter, so you're only looking at overall distance traveled, then this can be used. Okay, so or overall distance, okay, where you don't care about the direction. And it allows us to read the graph and determine distances at any specific time. So I could say to you, what's the distance at 2 seconds? And you'd say to me, well, that looks like it's this point here, so that must be 10 meters. So the distance at 2 seconds is 10 meters. And we can also calculate the slope of the distance time graph to determine speed. And that would end up in meters per second. And I want you to consider for a second how we know for sure that the slope is meters per second. Well, slope is rise over run. And that in our normal math world, we'd say it was the change in y over the change in x. And in our case, y is d. So what we have here is the change in distance over the change in time. And look at your unit analysis. Change in distance, that would be in meters, and time would be in seconds. So we have meters per second, which is a speed. Okay? So we're looking at being able to calculate a couple of things fairly easily. Now we're looking at a similar set of notes for position time graphs. Remember the difference between position and distance is position is a vector, so the direction matters. We still have a vertical axis, so it's representing the same idea. So it's position on the vertical axis. So if I were to draw one, sorry about that, if I were to draw one, then this would be the position, and this would be the time. So you can see it's pretty similar. All that's different is the vector. And this time we can only represent motion in one dimension. So that is motion in a straight line. So forwards and backwards, that would be a straight line. Or north and south, that would be a straight line. Or east to west, right? So we can go in two directions as long as they're opposites of each other, right? Those directions would be opposites of each other, but the motion occurs in a straight line, so we can use a position time graph to represent this. It also allows us to read the graph to determine position at any specific time, just like we could determine distance before, and that means we can also calculate displacement between any 2 points, just like we were doing in the calculations in the previous lesson. So if I know, let's say I know position 2 and I know position 1, I can find the difference between them, and that gives me a displacement. Right? That will give me the change in displacement between points 1 and 2. Okay, so we can do that from the graph just like we could algebraically, and we can calculate the slope of the position time graph similar to the distance time graph, and this time it will result in a velocity, right? So it'll still result in meters per second by finding the slope, because we still have meters and seconds as our units here, and this time it'll come with a direction. So whatever direction the displacement had, the velocity will have the same direction, as long as we're going in a positive direction at that time, right? So the directions are related. So we're going to do an example here where we create a graph from a description that's given. So here we're using an example where Natalie's taking a bus to school, and the school is obviously west of her home. The ride is 5 kilometers and takes her 30 minutes. She stays at school for 7 hours and then takes the bus home. We're going to use her home as the origin. So that means that position 0 is her home, right? So D0 is home. So that has to be 0 kilometers. Okay, so we're just going to graph this. So if home is the origin, that means the graph starts at 0, 0, and in the first 30 minutes is going to go up 5 kilometers. So let's assume that this here is our position, and we're going to do it in kilometers. And she's heading west at the start. So let's use west. We have to define a direction. You could use east. Your graph would vary a little bit, but you just have to make sure you definitely define something. And we know this is time, and we're going to do that in hours. So in the first 30 minutes, you have to excuse my rough graph, it's hard to draw a straight line on here. So we end up with a straight line between 0, 0 and 0.55, because she ends up 5 kilometers away within half an hour. So now for 7 hours, and I'm going to actually do this in blue so you can see it really clearly over top of the graph. Okay, we end up for 7 hours, so that takes us 7.5, staying at school. So her position is staying the same. She's at school that whole time, and then she heads home, and home is east, so that means that we're going to be going downward because she's going back towards home, and we know home is position 0. So we can use this to find positions just like I talked about before. So we can say that what is the position for at 0.5? Well, the position at 0.5, we can read the description, we can look at the graph. Look at the graph, you can see that's that point there. So the position at 0.5 is 5 kilometers west. And again, remember that direction is really important. What about the position at 4 hours? Well, we look at 4 here, and we go up from 4, and we see that that's this point here on the graph, so that's still at 5 kilometers west. And actually that would be the same for 7.5. Right, so 7.5, that's when she starts to head home, so that's here. And then at the end of the day, she gets home. That's this point here. And we're back at home for that 0 kilometer mark, back to where we started. We can use these to find displacements, just like you did algebraically. So if we wanted to know the displacement between from 0.5 to, let's say, to 7.5, we'd end up with 5 kilometers minus 5 kilometers, and they're both west. So we get 0. So the displacement during that time, between half an hour and 7.5 hours, the displacement is 0. So that means in that time, she is at the same place that she started. We could also look at, let's say, the position or the displacement between 7.5 and 8. So that means we're doing the position at 8, which we know is 0 kilometers, minus the position at 7.5, which is 5 kilometers west. And remember that subtracting is the same as adding the opposite direction. So this can be written as either negative 5 kilometers west or as 5 kilometers east. Okay, both answers are correct. And basically this tells us that at the 8-hour mark, she's 5 kilometers east of where she was at the 7.5-hour mark. Just to quickly think about that scenario, what if the school was the origin? So instead of home, it was school. I still put west here at the top of our graph. Okay, and we're just going to, you're going to notice I've drawn the graph already for us. And it looks like the graph has just been shifted down by 5 kilometers, and that's exactly what has happened, right? The motion itself hasn't changed. She still ends up going at the same speeds, at school for the same time, so the shape of the graph should be the same. The location of the graph merely depends on where we define the origin to be. So there's nothing special here. If you were to calculate some of the similar displacements that we looked at on the previous slide, you should find that you get the same answer. You can try it if you're unsure, but we'll get the same answers that we did before. This time I've given you a graph, and we're going to create a little chart that would be used to describe that motion. This is essentially what you have to do if you have to create a story. So if you gave you a graph and said create a story or a question to go with it, you'd have to understand these aspects of the graph before you can actually create the story. So sometimes I'll ask you to do this. So here we'll start with part A. So you'll see part A runs from 0 seconds at 3 meters and stays at 3 meters north specifically until 2 seconds, right? We've got this straight part of the graph here. Okay, and we want to be able to describe that straight part of the graph. So what direction is our object or person traveling in here? Well, the position here is staying constant, so it doesn't really have a direction at this point. So you could put one, but you don't really need to. So I'm just going to put a little dash here to indicate that I know that there's no direction. And we can look and see it's staying in the same position. So if it's staying in the same position, it's not moving, which means there is no speed. So I can put 0 here, just to say it's not moving at all. Now in section B, this is the positive part of the line here. Okay, we're going to do the same idea. So now it's going downwards in this direction here. So how would my position change? Position is going from 3 meters here to 0 meters here. So if I did my position calculation for that, I would end up with 0 minus 3 meters north. So what I actually end up with is negative 3 meters north or positive 3 meters south. So the change that we're getting here, the direction that the person or object is heading in, is in the opposite direction that we can see there. And you can figure that out by thinking about the slope too. The slope of that line is negative, therefore the direction is negative, and since north is positive, that means we've got our negative direction, or in this case, south. And we want to know what that speed looks like. And to describe the speed, all you need right now is to tell me if it's constant speed, if it's speeding up or slowing down. And we're looking at this and we can see it's a straight line. So it seems the object is going at a constant speed. So here I'm just going to put constant. So you could have put constant for the one above it as well, right? We could put constant here because 0 is constant as well. Okay, so we're putting constant. All right. And then part C, you can see the line still seems to have the same slope. It's just gone below the 0. So I wanted to separate them because that becomes important when we look at other types of graphs. But you can tell that this slope is still negative, and as I explained before, if the slope is negative, then the direction is negative, and negative here is south. Remember, because positive is north. So negative is south, and it still seems to have this constant speed because it's a straight line, so it's constant. And then part D, we have a line still in the negatives here, but now it's going upwards, right? It's going back towards 0, so that means the slope is positive, right? We're going back towards the positive direction. So it might be in a position that's behind the origin, but it's heading forwards. So now we have a north direction, and again it's a straight line, so the speed must be constant.